Hello, welcome everyone. We're going to wait a couple of more minutes just to wait for any more participants that will join us. Well, hello, welcome everyone. Welcome to this brief webinar discussing the main factors and the main variables that we need to take into account when designing and when optimizing a microseismic, seismic or acoustic emission monitoring array. My name is Juan Reyes Montes. I'm a consultant at appliedseismology.co.uk, and I will guide you through this webinar. I forgot to say, there is a chat where you can post your questions, and we will try and cover them at the end of the webinar. Okay, so which part of the whole data processing flow, microseismic data processing flow, are we presenting today? Well, we are discussing what would be the initial part of any microseismic or any acoustic emission project, which is designing, optimizing the position of our sensors, our stations, depending on the scale we're working on, so that we can meet the objectives of our project. We can see that, we will be at this initial state, but it also might occur after the initial monitoring, because it's always a process that we can optimize. We can get back to it and try and improve the performance of our array by changing the configuration, adapting, changing the position, adding more stations onto it, depending on whether we are accomplishing the objectives of our project, of our job. So, even though we presented this as microseismic, seismic, or acoustic emission array design, there are some differences in between the different scales we're going to work on. And I'm going to start discussing what will be the main design considerations that apply to what would be a microseismic project, that it's reservoir scale seismic monitoring, almost local scale monitoring project. And a very important consideration in this case also applies to larger scale seismic monitoring, would be the accessibility. Would be where can we access to safely install and position our tools, whether they are downhole tools or surface stations. Also, in the case of the lab, and we will see that later, we need to consider where do we have access to position our sensors. So this is a point that needs always to be considered. And of course, the very critical in every project is the cost. because we can, if there's no limitation in cost, yeah, of course we could instrument our project to infinity and get an optimal, very good results, but we need to be realistic and fit a budget, usually, that we need to meet for the project. And of course, very important, the objectives of our job. So, the size and the position of our target volume, the range of events that we are interested in, so whether we want to be sensitive to really small events, or we might only be interested in events that can be felt or that can cause damage. So depending on the detail that we want, we can optimize the design of our array. Also, what would be the optimal desired accuracy? Of course, we always want to have the maximum accuracy, but yeah, we need to come up with a figure that will be sufficient to meet the objectives of our job. And of course, a final point will be what are the source parameters that we are interested in obtaining, in monitoring. It's not the same. We might be simply interested in getting a count of events, in which case, yeah, we just one sensor will be enough to detect an event. If we want locations, then we have a minimum number of sensors, typically 3 or 4. We will discuss that later. And if we want more details, if we want to obtain source mechanisms, etc., we might enhance both the coverage of our array and also the number of instruments that we're using in our locations, in our processing. So, what are the variables that we have to play when designing and when creating a seismic array? Well, the first one is the type of instrument we want to use, the instrumentation that we have, both the response, the sensor type, whether it's responding to displacement, acceleration of velocity, and also, of course, very important, the dynamic range and the frequency response. And this is also connected to the size of our target volume and the range of magnitudes that we are interested in monitoring. A second variable is, of course, the number of instruments. So, yeah, we can, when we are working on the design, we can see the impact of increasing or reducing the number of instruments that it has on the results of our monitoring. And very important is the position of these stations or sensors, depending on the scale we're working on, the geometry. And in the case of a field, the standard will typically work with either a borehole array, which will have a linear configuration, a planar array, typically on the surface, so an array of surface stations, or not so feasible in most cases, but ideal if we want to get robust results, especially if we are interested in acquiring source mechanisms, a three-dimensional array that is combining borehole instruments with the surface instruments, or instruments are positions along several boreholes. So, number of stations, why is it critical? Well, in principle, as I said before, we can work with a single station, and a single station might give us results for location if this single instrument is a triaxial instrument, has more than has 3 sensors at least, and yeah, this in principle is enough to produce a location, but typically requires manual processing, and also it's not a very robust solution. a larger number of stations is always needed if we need a calculation of any other source parameter, that it's not purely location, or if we want to automate the process and make it more robust. Also, because usually not every station that we have in our array can be used in the processing of our events, then we might need to increase the number of stations just for redundancy, basically, to make our results more robust. And there are many factors that might make waveforms unprocessable, basically, that might make our tool unusable in the case of a particular event. The most typical, it's distance, separation to the source. But also, of course, there could be some transmission operational problems such as noise, the presence of voids or highly attenuating bodies in between a particular station and the source, and any source of noise that positions near our sensor or our stations. And in fact, some intrinsic noise sometimes, so our sensor can be a source of noise itself. So, for all these reasons, it's always recommended that we install a number of stations larger than the minimum required for the automatic processing of whatever parameters we're interested in. The second factor that we discussed here was the geometry, and we can see here a sketch of the impact of geometry in our monitoring. The spatial distribution of the seismic stations have a very direct impact in the sensitivity and also the performance of our array. Basically, the coverage that we have, the distribution of our sensors, have a direct impact on factors as important as the convergence of a location algorithm. That is, if we have our stations providing a poor coverage, our location algorithm might not converge, might not come to a single solution. There will be multiple possibilities for our location, and that makes our processing not robust. Also impacts on the uncertainty in our location, of course, in both the geometry and number of stations. Also, if we have a small number of stations, they might not be robust against effects such as shadowing, that is, the presence of a void or the presence of some non-transmissive body that will basically block the use of certain stations. And also a very direct impact in the sensitivity, the magnitude sensitivity. That is, what is the smallest magnitude that we can detect for an event. And here in this figure, which is just an illustration of the impact of using a downhole tools or a surface array for the monitoring of, in this case, is the development of a reservoir for energy. And we can see very clearly here the impact on the magnitude threshold, that it's the smallest magnitude event that we can detect using either array. And we can see that, when stations are positioned very close to the source, we can detect small magnitudes, in this case up to -2, while if we position them on the surface, that would be, in this case, probably around 2,000 meters above our target area, we are less sensitive and we can only detect the smallest event that we can detect is around 0.15 or so. And why is so important was that we get the right geometry? Well, we discussed before that our location algorithms might not converge, and this is just an illustration of a case in which we have our tools positioned down a borehole, and in the case that we are not using source vectors, then our residual space, which is what a location algorithm uses to come up with what would be our solution, what would be the location of our event, look like. And we can see that the minimum, that would be the solution, well, it's not unique. Our minimum is not unique, and we can have multiple possible solutions. In this case, the white dot will represent the true position of our source, but as we can see, our algorithm might find multiple solutions in a radial distribution around our tools. If we have a two-dimensional array, as we have here in the bottom, well, in this case, our solution is unique, becomes unique, and our location algorithm will converge and will give us a robust solution. And this is just another illustration of what would happen if we not only use travel times, but we also use source vectors. In this case, the shape of our residual will converge, will likely converge to the true position. Still, we can see there's a large residual, and that fits into the uncertainty, the inherent uncertainty that we have for the location of our events. So, again, talking in the case of the field, what would be the advantages and disadvantages of using the different usual configurations? In the case of a downhole, of positioning our tools down a well, downhole, there are clear advantages. The noise levels are much lower because we are far from the surface, far from any interference from surface noise. So we'll have definitely low noise levels. Lower attenuation because we are closer to the source. Basically, the travel distance is shorter, so we'll have a lower attenuation. We will typically get a very good depth resolution with only a few stations because, well, basically we are again positioned around our target with tools positioned at different levels. So depth will be very well resolved in this case. And, well, we can monitor in this case for the full treatment if we position our tools in a monitoring well. There are, of course, disadvantages to this. One clear one, it's that we need, this is like I say all the time, but we need to ensure that the clamping is good in between the well and the tool. So our tools are basically glued, well, not glued, but well coupled with our well, so there's no dissipation and no attenuation of the signal. There's a potential always for noise from the pumping if the wells are close to each other, and yet we need to make sure that we are not too close to the source, because in this case we have what we call the near field effects. And yeah, there are several of them. One very clear is the overlap of the different phases if we are not too far from the source, and we might get an overestimate of the triggers in this case. Or having a linear well provides a very poor azimuthal coverage, which we might need to supply with additional information such as source vectors. If we can position our tools in the treatment well, we have basically the same advantages as being in a separate monitoring wells, being deep, close to the source at relatively low noise levels, but we'll discuss this later. But very clear disadvantages. One of them is that we cannot monitor during injection. We need to wait until the injection has finished because of the basically the noise levels and the high pressure that it causes. There's a risk to our tools because there is fluid being injected. There are high pressures that will require our tools to be able to withstand high pressures and be robust against this. As we are closer to the wellheads, in this case it's more prone to detecting noise from the surface, and as the same disadvantage that we had before, again very poor azimuthal coverage. So a solution to the problems that we have with downhole tools will be positioning our tools on the surface, which have one thing is a clear advantage is that they are very easy to position. It's normally much more cost effective. So we don't need monitoring wells, we don't need high pressure temperature condition tools, and our coverage, our azimuthal coverage is usually quite good, right? Because we can basically position our tools around our source. The disadvantage is that we will typically need a large number of tools spread over a very large area, and the rule of thumb for this is that they have to have a span of as wide as the treatment depth that we want to monitor. There is a very high attenuation because we are far from the source, and also, well, typically the geology is more attenuating at the surface than at depth. High environmental noise because we are again close to the source, which is typically affected by this, and a very poor depth resolution because we are at a single level. We are listening from a single level. So best of both worlds would be a shallow well, in a way, because, well, they are more economical, so we don't need a deep well to deploy our tools. We don't need our tools to be robust against high pressure and temperature. They can be deployed permanently, and still they have reduced noise if we compare with tools that are positioned on the surface, because they are away from the source of noise, and also the geology is less attenuating. The disadvantage of this, well, we are still a bit far from the source, so there will be a low signal to noise, and also the poor depth resolution because we are again deploying our tools in a single level. Another consideration that we need to take into account is the bandwidth of our tools. This, well, also depends on the type of tool that we have, but also on the electronics within it. And this is just one of the effects of our bandwidth. And we can see here what would be the spectrum of events of different magnitude. We can see that a small magnitude event, they have a high corner frequency. These high frequencies are easily attenuated. So in this case, we will need, if we're interested in monitoring events of very small magnitude, well, what we will want to have is an instrument that is sensitive to these high frequencies. Typically, we can see here, we would use this 15 Hertz instrument for them. Because basically it's flat, has a flat response above it, and well, below it there's not much energy because most of our energy is in the high range of frequencies. And we're talking high frequencies here, it's anything above tens of hertz in the field. So we will think this is the optimal instrument, but well, it has a disadvantage because we can see that if we are monitoring also, or we are expecting high magnitude events, any event basically with a positive magnitude, or magnitude of 0, then we can see that if our instrument is sensitive, is flat above 15 Hertz, for example, then it will typically have a decay for lower frequencies, and we will be underestimating the energy of our event. It's what it's called the magnitude saturation. That it's our events will have an underestimated magnitude, just because we are not sensitive enough for this low range of frequencies. By low, we're talking about hertz or below. So, if we want to be sensitive to a small and large magnitude events, we'll be interested in a broadband instrument, typically with a natural frequency around half a hertz or 0.7 hertz, as we can see here. So, this is a consideration that we need to take into account at the beginning when we are planning our array. What is the range of magnitudes that we are expecting, or we will be interested in monitoring? Totally different range of frequencies we're going to talk now. All the considerations that we mentioned before, geometry, etc., they affect any scale that we are monitoring. But when we're talking about acoustic emissions, we are dealing typically with much higher frequencies. We are in the range of the kilohertz or megahertz, and we are using different instruments in this case. And this is a typical instrument that we use, are transducers, piezoelectric transducers that typically consist of a crystal that has a critical temperature, we can see here. So we need to consider, take into account what are the settings of our experiment, the experiment we are monitoring. Because, well, if we are working at high temperatures, we might be affecting the sensitivity of our crystal, the sensitivity of our sensor. So that's a consideration that we need to take into account initially when instrumenting a lab test, a lab experiment. So the choice of our sensor is critical. Very important, the frequency response of not only our crystal but the whole acquisition system. So we need to make sure that our amplifiers, our acquisition system, and our crystals, our sensors, are all well coupled, are all, when put all of them together, they can operate. The actual frequency response is sensitive to the range of magnitudes we are expecting from our events, and that they are robust against the conditions of our test. By conditions, I'm talking about pressure and temperature conditions. And, well, this is just very quickly showing here what are the frequencies that we are interested in. Well, it's the frequencies that we need our sensors to be to have a flat response, basically, so that we can not only detect but provide a good reading of the amplitudes in our event. And, well, this is just a back of the envelope calculation, but if we're talking about granite, for example, which has typically a very small grain size that goes in between a few fractions of a millimeter up to a few millimeters big, and we want to detect what would be the breakage in between crystals. We will want to have, in this case, an instrument with a corner frequency, basically covering the frequency of something in between 1.5 and 2 megahertz. Of course, we need to work with a wide bandwidth. So the minimum bandwidth required has to be cover above this corner frequency and below it. So we want to have what we call the 3 decibel band of about, in this case, what is recommended, it's around 7.58 megahertz. So, yeah, these are the considerations that we need to take into account. It depends on the expected, what's the smallest event that we expect from our rock. It depends on the type of rock that we are monitoring, and it depends, of course, on the size of the sample that we are looking at. And, well, just a quick calculation of what would be the expected error, and the error here is just based on us being able to capture what would be the arrival of our acoustic emission event, and that it's basically linked to what would be the rise time. So we want our sensor to be able to capture in full this arrival, and if there's any distortion to it, then we can calculate what will be the error in estimating that arrival. And we can see here what will be the minimum bandwidth and what will be the optimal bandwidth that we need to have in our sensors. Of course, the wider the better, but, well, here we can see if we are monitoring very small events, we're dealing here from 0.3 millimeters to tens of millimeters, we would expect to have a bandwidth, a minimum bandwidth that we have here. See the effect of this. Okay, so this is going to show what is the typical exercise that we do, which would be modeling the performance of our array. And what can we model? Well, we can model the type of tool that we have, we can model the configuration, that will be the geometry basically of our tools, the number of tools, and where do we position them. And in the model, we typically work with producing what with the smallest, the magnitude threshold, that it's the smallest magnitude event that we can detect with our array. What would be the shape of our residual if we want our location algorithm to perform well, and what is the estimated location uncertainty. And this is something that, well, I'm going to open our seismic processing software inside, and it's something that we can easily model in inside. In this case here we have an acoustic emission test. It's a cylindrical sample of rock, and we are modeling granite in this case. By modeling granite, what I'm talking about will be the velocity, the propagation velocity for the waveforms. So, a typical analysis will involve, as I mentioned before, analyzing what would be the magnitude sensitivity. What is the smallest acoustic emission event that I'm expecting to detect across our sample? We can see here the variables that we use. Well, typical variables will be what would be the expected signal to noise ratio. What would be the signal to noise ratio I want our signal to have if we can detect our event? What is the attenuation, the Q factor, attenuation in our rock? What is the minimum, that depends on the sensitivity of our tool, what is the minimum velocity in this case that can be detected by our sensors, the expected stress drop, and of course the density of our rock. I'm going to run this simulation. We can see here, what is the typical output. The output is, I'm going to close this, it's just a map, a density map. I'm going to show the properties. That it's basically telling me that, yeah, this configuration that we have here, which is a very good one, because, yeah, we have 18 sensors almost evenly distributed around our sample, will give a quite, well, always, of course, more sensitive in the center of our array, in this case in the axis of our rock sample, we'll lose sensitivity towards the edges because, yeah, we get closer to a single sensor and we don't have as good coverage from the rest. But in general, we can see that across our sample we are able to detect events between -6 and -6.5. In this case we're talking about instrument magnitude, it's not absolute magnitude. So ideally what we want to have is a homogeneous coverage, and which is almost what we achieve in this case. And also, if we are interested in a particular area of our sample, if we are injecting, for example, in it, well, we might want to increase the sensitivity around there. So, yeah, this is one of the typical initial study that it's carried out. I'm going to show that, again, it can be done in the context of field monitoring. Same situation, only that in this case, of course, we are working with slightly different parameters. But, yeah, I'm going to launch it. And we can see in this case, well, it's not such a homogeneous coverage because we're working here with a vertical array. Our tools in this case are all along a borehole, a bit far from our target volume, and we are only listening from one side of it. So yeah, if we look at the oops, yeah, oh, it's not launching properly. Yeah, so yeah, we have very sensitive as we get close to our tools, and well, there's almost like a yeah, 3 magnitudes of difference in between our tools and the volume that we are interested in monitoring. So 3 orders of magnitudes we lose from our tools, but that's something that we cannot avoid in the field unless we position tools on the other side of our injection well or on the surface to provide a better coverage. But yeah. So another typical study, once we've looked into what would be the sensitivity of our array, I'm going to yeah, I'm going to hide this. The next typical analysis is what we call the misfit space. That is just the shape of our objective solution or objective function, that it's the residual. So I'm going to launch it, just to display, and in this case I've positioned a theoretical event at the center of our sample. I'm going to close this, and we can see that if I show this, minimum, it's good actually, it's well positioned around the theoretical position of our event. It's a well-defined minimum, it's a single minimum. So in this case we expect our location algorithm to be robust. Don't have any difficulties in defining the solution because yeah, it's a well-defined, it's a single solution, and it's yeah, robustly located there. I'm going to show here what will be. It's almost, well, I'm going to work. What would happen if we have a linear array and we're working only with travel times? Well, in this case, if we carry out the same study, well, we can see that our solution is not so well defined. It's, yeah, there's almost like a 360-degree uncertainty. That can be solved through the use of source vectors. But what it's telling us is that using only travel times will not give us a robust solution in this configuration, in this case. So these are the two main studies that we need to optimize. And of course, if the solution is not our desired solution, we would modify the geometry, we will modify the configuration of our array until we find what will be the optimal solution. Finally, another study that we can carry out is what is the expected error in the location of our events. So, I'm going to hide this. So, for example, if I have an event located at this position, what is expected error uncertainty that I will have when locating and actually getting all the parameters for this event? Well, a very easy way to analyze this would be a simulation, a Monte Carlo simulation, in which we basically introduce an uncertainty in our velocity model, an uncertainty in our peaking in determining the arrival of our P wave, and, well, randomly add this uncertainty to the theoretical arrival and carry out location and inversion, in this case 100 times, just for speed. It should be pretty quick. It says it takes about 10 seconds. So what it's doing is creating what would be a theoretical travel time, then adding the noise onto it, the noise being the uncertainty in the peaking and the uncertainty in the velocity model. So what we're getting here, it's potential locations for our event, which would be in the black dot there, and these are the potential locations for it. And this ellipsoid is giving us what would be the error ellipsoid for a location at that position. We can see that even there's a likelihood of some locations being at 180 degrees from it. That's just basically because, it's very easy to come up with what would be the reversed polarity if we don't determine well the arrival of our P wave. You can come with a reverse polarity, and some events will locate 180 degrees from the true location of our event. We probably don't have, and we definitely don't have that difficulty in a three-dimensional array. I'm going to carry out the same simulation here. I'm going to reduce it. This is much faster. And in this case, almost all of them fall within a few millimeters from our theoretical position. And this is just purely based on the fact that the attenuation is much smaller, and also we have a very good coverage. We have more instruments positioned in a three-dimensional distribution around our source. So this was a very quick overview of the factors and the analysis that you can carry out to optimize and estimate the performance of a seismic array. There's of course much more detail that we can cover, such as what would be the ideal bandwidth of our sensors. These are all part of future webinars that we will discuss in more detail. This was an introductory webinar, and I hope it covered what you expected to see from this presentation. If you have any questions, please leave them in the chat, or get in touch with us at our email, asc-info@appliedseismology.co.uk, and we'll be very happy to discuss with you any of your questions in more detail. Thank you very much for your time, and hope to see you in the next presentation.